In the previous example, or in the previous video, excuse me, we were working on this problem. How fast is the radius changing when the circumference is 6 centimeters? And unfortunately, we ran out of time with the video. So let me finish this off. Now remember, we had two formulas. We had area is equal to pi r squared, and we also had that the circumference is equal to 2 pi r. And we did go through and we said that the circumference is 6, which is equal to 2 pi r, and that means that 3 over pi is equal to the radius. We also had this relationship that dA dt is going to be equal to 2 pi r dr dt. And the problem says how fast is the radius changing? All right, so remember we took the derivative and we said, well, dc dt is equal to 2 pi dr dt. But we don't need that because we're not looking for the change in the circumference, we're looking for the change in the radius, which is actually going to be this animal right here. And so since we know r is 3 over pi, and we know that dA dt is going to be equal to 5 centimeters square, we can rewrite this and we can say that 5 centimeters square per second is equal to 2 pi times 3 over pi centimeters. All right, and remember the radius is just measured in centimeters, times dr dt. All right, so I just substituted for r, substituted for dA dt. Pi's are going to cancel out. That just becomes 6 centimeters. So we have 5 centimeters square per second. So let me erase this, make it look legible as much as I can. So 5 centimeters square per second is going to be equal to 6 centimeters dr dt. And since we're trying to solve for dr dt, we're going to divide both sides by 6 centimeters. And so what do we end up with? Well, we end up with 5 over 6. We have centimeters squared over centimeters, and the seconds just stays in the denominator. So this is going to be centimeters per second is equal to dr dt. All right. So another example. The edges of a cube increase at a rate of 3 centimeters per second. How fast is the volume changing when the length of each edge is 40 centimeters? All right, so this is actually a pretty straightforward problem. We have a cube, and we know that the volume of any cube is going to be any of the sides cubed, which is why it's called a cube. And so we know right away that the edges increase, and we want to know how fast is the volume changing. All right, so we're just going to find the derivative. So the derivative of v is 1, and then we multiply by dv dt. The derivative of s cubed is 3s squared, and we're going to multiply that by ds dt. Now the edges of the cube are changing at 3 centimeters per second. All right, so that's going to be our ds dt. And right here is going to be our s, because that's the length. And we're just going to substitute everything back in. Right? So be careful with this. So we're going to have dv dt is going to be equal to 3 times 40 centimeters squared, or centimeters quantity squared. And then we're going to multiply that by ds dt, which is going to be 3 centimeters per second. All right, so what does this work out to be? Well, we're going to get 9 from the 3 times 3, and we're going to get 1,600 centimeters squared. So we're going to end up with dv dt is going to be equal to, and I don't have my calculator with me, so 9 times 1,600 centimeters squared times centimeters per second. I know 9 times 16 is 144, so dv dt should be equal to 100, or 14,400. We have centimeters squared times centimeters, so that's going to be centimeters cubed per second. One last example. Circle has an initial radius of 50 feet, and we're decreasing this time at a rate of 5 feet per minute. What's the change in the area the instant that the radius is 10 feet? All right, so circle starts out with 50 feet, which is r. and the radius dr dt is shrinking. Okay, so that's -5 feet per minute. And what's the change in the area when the radius is 10 feet? All right, so let's go ahead and try to figure this out. So first of all, we're going to say area is equal to pi r squared. That's easy enough. We know that if we were to substitute 50 back in, we could find the area, but we really don't need it. All right, so in fact, I don't necessarily know if this 50 feet factors anywhere into the problem, but let's see if it does. So we're going to take the derivative, which we've already done, of both sides for the rate. So dA dt is 2 pi r dr dt. We know dr dt is -5. We know that the radius is 10. So actually, this is pretty straightforward. dA dt is going to be equal to 2 times pi times 10 feet times dr dt, which is -5 feet per minute. And this actually looks like it's going to work out really nicely to -100. So dA dt is going to be equal to -100 pi. And always note that my math lab wants you to put things into the exact form, so don't multiply it by 3.1415, whatever pi is. And then we have our feet times feet, which is feet squared per minute. All right. And again, have we answered the question? What is the rate of change of the area? All right. And since it's shrinking, it should be a negative. All right. So that should make sense to us. All right. So hopefully this overview of related rates isn't too difficult, and it makes sense, especially about the little tricks for the differentiation.